Good morning and welcome you all to this session of the course. Now today we will be solving some problems relating to axial compressors. Last class we discussed in brief the principle of operation and the degree of reaction of an axial compressor. Now today we will see that how we can solve problems and so that our understanding becomes much better. Now let us concentrate on one problem. This is the problem number 1 which we will be solving. The conditions of air, let me read out the problem first. The conditions of air at the entry of an axial flow compressor stage are P1 is given, the inlet pressure and temperature is given. The air angles are beta 1, so this nomenclature is known to us. This is the blade angle at inlet, and beta 2 the blade angle at the outlet, that is the rotor blade angle at the inlet and outlet, that is 51 degree, both are 51 degree, and alpha 1 is alpha 2 is 8 degree. This is given. Alpha 1 at the angle of the absolute velocity at the inlet and alpha 2 is the angle of the absolute velocity at the outlet of the rotor blade. So, the mean diameter and peripheral speed are 0.5 meter is the mean diameter and this is the peripheral speed respectively. That means the peripheral speed at the mean diameter. The mass flow rate through the stage is 30 kg per second. The work done factor is 0.95. All these things are known to us. Mechanical efficiency is 90%. Assuming an isentropic stage efficiency of 85%, what are to be found out? We have to find out blade height at entry, stage pressure ratio and the power required to drive the stage. This is given for air, the characteristic gas constant 287 joule per kg and the ratio of specific heat 1.4. Now, sorry, to find out the blade height at entry, first of all you have to understand that it is the geometry blade height which is basically related to the area at the inlet. So, therefore, if we write the equation of mass flow rate, that thing we have to select this equation to find this. We can write that rho 1 inlet density and the area at inlet and the velocity of flow which is same throughout. Now, here first of all we have to find out A, rho 1. Now, within A, that is the annulus area, the blade height is there. The blade height can be found out from the annulus area A. Now, let us find out rho 1. So, rho 1 at the inlet can be found out from the equation of state as P1 by RT1. Well, so P1 is what? P1 is given as 100 kilonewton per meter square. So, therefore, 100 into 10 Newton per meter square, 100 kilonewton into 10 to the power 3 P, and if you write the value of R 287 and T is 300, we get the value of rho 1 and rho 1 comes out to be 1.16 kg per meter cube. Alright, we get rho 1. How to get Vf? The flow velocity, is it given assuming an isentropic state? Air, the flow velocity is not given, but we can find out the flow velocity from the expression we developed earlier, that U by Vf is what? Tan alpha 1 plus, because we choose this expression, flow velocity is not given, but beta 1 and alpha 1 is given. So that we can find out the flow velocity at U. What is U? U is given 150 meter per second. So, 150 divided by tan alpha 1 plus tan beta 1, that means tan of 8 degree plus tan of 51 degree, and if you solve for it, you will get a velocity 109.60 meter per second. So, therefore, you can get the annulus area, but before that you put annulus area in terms of this blade height. Annulus area is pi into the mean diameter into blade height. True. Where from does it come? It comes that annulus area is pi into outer diameter square minus inner diameter. If you consider the inner diameter as the diameter of the drum or disc and the outer diameter is the diameter of the casing, then this is the annulus area. This can be written as pi into d0 plus di by 4, d0 plus di by 2 and d0 minus di by 2. Now, this is the mean diameter d0 plus di by 2 and this is the blade height. So, therefore, this can be expressed in terms of the mean diameter and blade height, that area. So, therefore, now if I substitute here, we can write m dot is given 30 kg per second is equal to rho 1 1.16 into Vf. First I write Vf because I have found out Vf 109.60 into pi. What is dash dm? Dm is given as 0.5 meter, okay, 0.5 meter it is given. So, therefore, pi into 0.5. So, only unknown is your blade height h, which gives h equals to rather h1 the blade height at the inlet. So, I write h1 blade height at the inlet. So, h1 is 0 equals to 0.15 meter. So, the first part is over, the h1 blade height at entry. How to find out stage pressure ratio? Stage pressure ratio is simple to find out. Stage pressure ratio to find out, what you have to do? You have to find out the static temperature, the stagnation temperature ratio or the stagnation temperature difference. Otherwise, you cannot find out the static pressure ratio. So, H1 is known. Now, let us find out, write this formula that Cp into delta T St, that means the stagnation temperature is equal to, today last class we have discussed that it is the work done factor into UVF by Cp is always there, UVF into tan beta 1 minus tan, where from it comes that this is the work done per unit mass, this is equal to Cp delta Tst. So, therefore, this is multiplied with a work done factor. So, here what we have? We have U, we have Vf, we have beta 1, we have beta 2. So, we can find out delta Tst. We can write this. What is the value of lambda here? Lambda is 0.95, it is given. Well, then the U is 150 meter per second. Vf we have calculated just now 190. I am sorry, Vf is 109. No, Vf will come out as 109. Yes, yes, Vf is 109.60. So, this is lambda U into Vf. Vf is 190.60. That is the Vf we have calculated, and tan of into tan of 51 degree minus tan of 10 degree divided by Cp. Now, Cp value you can calculate here. Here Cp is not given. Even if it is not given, you can take that. In this problem, gamma and characteristic gas constant is given. Cp can be found out as gamma by gamma minus 1. That means 1.4 divided by 0.4 into 287. That is the joule per kg. That means if you find out Cp, it will be 1005 joule per kg. This is the standard value of Cp for air. So, Cp, then you can find out delta Tst, and that becomes delta Tst becomes equals to, if you calculate it, I tell you the value 16.37 degrees Celsius. Then you can find out the pressure ratio Rs, as I have told that this is the nomenclature and this is the formula. Again and again we tell this will be 1 plus the isentropic stage efficiency, that is eta S, it is isentropic stage efficiency, delta this formula I have told, inlet temperature divided by gamma minus. Okay? So, this can be written as 1 plus this substituted the value substitute. If you can substitute the value, delta Tst is 16.37 divided by 300 and if you put the value of gamma, then you get the value of the stage pressure ratio as 1.17. Third one is that, what is the third one? The power required to drive the stage. Power required is very simple, because this is the Cp delta Tst. Cp delta power required is what? Power per unit mass into the mass flow rate. Mass flow rate into Cp delta Tst. So, delta Tst we know, this already we have found out, multiply with the Cp, that means this part. That means actually this part. So, this part we know, and mass flow rate already we know 30 kg given in the problem, 30 kg per second. So, therefore, if we put the value Cp, this one, delta Tst 16.37 degrees Celsius and mass flow rate 30 kg per second, you get a value of 548.39 kilowatt. If you be consistent in the unit, finally you will get this result. This is the power. So, this is one example that we can work with. Next, another problem I will tell you, where you have some idea about the degree of reaction. Okay. So, this problem is this: the preliminary design of an axial flow compressor is to be based upon a simplified consideration of the mean diameter conditions. Suppose that the characteristics of a repeating stage of such a design are as follows. That means a particular stage, these are repeated for different stages. Stagnation temperature rise is given. That means indirectly the work done on the fluid is given. Degree of reaction is given. Flow efficiency is given 0.5, but this is actually not flow efficiency. I think it will be better if you write it as flow number. Vf by U is actually flow number, sometimes they write at flow efficiency. However, flow number, blade speed, that means it is the ratio of flow velocity to the peripheral speed. Peripheral speed is also separately given 300, that means we get Vf, multiply 0.5 with that. Then what is the problem? Assuming constant axial velocity across the stage and equal absolute velocities at inlet and outlet, that means V1 is equal to V3, that we have already done. Determine the blade angles of the rotor for a shock free flow, that means there is no incident loss. So, how to find work out this problem? Now, this problem if you work out, you see that the degree of reaction is given. Now, first of all we know the stagnation temperature rise. So, first of all we find out the work per unit mass is equal to, is known, that is what? That is Cp into delta Tst. And what is Cp? Cp is 1005 joule per kgK, and that is 30, and finally this becomes equal to your work per unit mass. Now, how to find out beta 1 and beta 2? So, what we have to find out? We have to find out beta 1, we have to find out beta 2, the two angles. Okay? You remember that beta 1, beta 2. So, I tell you again that this one we have to find out. We have to find out beta 1, beta 2. So, what we will do? We will take some of this relationship, tan beta 1 minus tan beta 2, tan is equal to work done. Where you will get that formula? That Vf, okay, I am coming to it again, it was done earlier. If you remember that W by M is Vw2 minus Vw1 into U, and that becomes is equal to U into Vf into tan beta 2 minus tan beta 1. Now, we know U, we know Vf. Vf is 300 into 0.5, U is 300, U is 300 meter per second. Well, and you can see, I think you can see very well, and Vf is 300 into 0.5, that is 150 meter per second. Tan beta 2, tan beta 1, beta 2 and beta 1 we have to find out. W by M we know. So, therefore, if we put this here and this value here, we get a relationship tan beta 2 minus tan beta 1 equals to what? Tan beta 2 minus 0. You get, everything is known. Now, we have to get another relationship relating beta 2 and beta 1, that will come from the relationship of degree of reaction. Now, degree of reaction, if you remember, is given by U by Vf. Degree of relation is Vf by U, Vf by 2U. If you remember that today we have done it, or last class we have done it, tan beta 2, tan beta 1 plus beta 2. So, we have done these things. So, here also we know Vf by U. Vf by U is 0.5. That means 0.6. That means, rather I write here, it will be better. 0.6 is 0.5. Vf by U is 0.5. It is given in the problem by 2 into tan beta 1. So, it is a simple problem which gives a relationship tan beta 1 plus tan beta 2 is, it is what? 1.2 to 2.4. It is very simple. So, this is one relation and this is one relation. So, as simple as this, and finally, if you solve for tan beta 1 and tan beta 2, finally you get beta 1 is 56.92 degree and beta 2 is 40.86 degree. These are the answers you can check. So, therefore, with the degree of reaction, you can, that is only that we have to deal with the equations, which equations will be required depending upon the parameters given. So, these are the problems which makes your concept more clear. Now, after this I will start the fans and blowers. So, fans and blowers, there is nothing much different from that of compressor. The difference is like this, that as I told earlier at the beginning of my fluid machines class, that when the output for a compressible flow, for example, that handling air, at the outlet of a machine where energy is given and we get the fluid at the outlet of the machine having higher energy, acquired stored energy, if that is mostly in the form of high pressure, static pressure, but less velocity, we call it as compressor. Whether it is centrifugal, it is axial. But when the basic purpose is to have fluid with very high velocity, where we have to deliver high rate of flow with high velocity of flow, therefore, there the machine must deliver the fluid with higher energy by absorbing energy from outside, mostly in the form of the kinetic energy with high velocity, but relatively much less pressure, static pressure. Those machines are known as fans and blowers. So, fans and blowers and compressor are same kind in a sense that they take energy from outside and the fluid flowing through it gains its internal energy. But for fans and blowers, this energy is mostly in the form of kinetic energy rather than pressure. Static pressure is more of velocity rather than static pressure. Now, amongst fans and blowers, fans are those machines where the static pressure at the outlet of the machine is few millimeter of water gauge. You can understand that atmospheric pressure is 10 meter of water gauge. It is so less, few millimeter of water gauge, whereas in case of blower, it is something more than 1000 millimeter of water gauge. Still it is very less, 10 meter of water gauge is the atmospheric pressure. So, this is the pressure, gauge pressure, that means above the atmosphere at the outlet. Why this pressure is so low and why the pressure is required? First of all, pressure is required because these machines deliver air for some purpose, that means air has to flow. It may be required that to supply the air through a duct. So, therefore, we have to overcome the friction of the duct. That means this flow has to take place through a duct, it has to overcome the frictional resistance, not only through a duct, through a room. So, therefore, downstream resistance has to be, frictional resistance has to be overcome to deliver that flow. So, these machines develop that pressure sufficient to overcome the resistance. Now, in case of blower, it handles more amount of air, where less amount of air is handled and is circulated or being sent through a duct. we employ fans, for which the frictional resistance is less. So, therefore, a relatively less static pressure is required at the delivery end of the machine. Whereas, in case of blowers which handles more air and at a high velocity it may have to be conveyed or transported through a long duct, the frictional resistance is much more. That means it has to overcome more frictional resistance so that the pressure drop is more. As a consequence, the static pressure at the outlet of the machine has to be higher. This is the reason for which blower static pressure is higher, because it handles more amount of air. So, this is the difference between blower and a fan. So, fan and blowers are basically the compressors, but in this case the static pressure at the end of the machine is much lower as compared to its velocity. Okay, thank you.